Okay guys, let's cosplay Euler. Okay guys, so let's get right into it. We're supposed to evaluate the infinite sum of the reciprocals of consecutive squares of integers, so the sum as n from n being equal to 1 up to infinity of 1 over n squared. I'm gonna show you guys the proof that Euler conducted in 1734, I believe it was. Well, I'm not gonna be really telling you guys how he came up with the idea for the proof, because I have no idea and probably no one has an idea about it. But I'm just gonna show you guys the proof to visualize, I guess, how beautiful it is. So, first of all, we are gonna come up with, pretty much out of the blue, the Taylor series expansion for sine of x. So the Taylor series expansion for sine of x is gonna look something like this. It's gonna be x minus x to the power of 3 or all over 3 factorial plus x to the power of 5 all over 5 factorial minus x to the power of 7 all over 7 factorial. That's gonna be just extending infinitely long. And you probably know this guy from your Calc 2 lectures. It's a pretty famous sequence. Okay, so, what can we do with it right now? Well, we could, for example, divide both sides of this equation by x to get the Taylor series expansion for sine of x over x. And y you're gonna see in a few moments. That's gonna be 1 minus x squared all over 3 factorial plus x to the power of 5 all over 5 factorial minus x to the power of 7 all over 7 factorial to the 4 to the 6 power and all the way up to infinity. Lovely. So what I would like to do now with this guy is to factor it into just a product of binomials. Well, by the fundamental theorem of algebra, we know that every single polynomial out there we can just go on and we can just go on and factor into a product of some binomial coefficients or some binomial terms, like I've drew right over here. And so we can do just the same thing with the Taylor series expansion of sine x over x, because, well, this is just a regular polynomial with, well, not really integer coefficients, but nobody cares about it. Okay, well, one more thing. Well, we see that whenever we factor out some kind of polynomial, let's say we want to factor x squared plus 5x plus 6, for example. When we factor it, it's going to be x plus 2 multiplied by x plus 3. And we see that the constant term right there, so the constant term here, is the product of those free-flying constant terms inside of those binomial coefficients. And so we see that the constant term is going to be the product of those constant terms inside of the binomial coefficients. Well, it's pretty interesting because we know that here in our sequence, the Taylor expansion for sine x over x, the constant term is equal to 1. And so the product of all of those constant terms inside of those coefficients, yeah, is going to be equal to a 1. So unless we want to, well, just multiply a bunch of fractions, which we probably don't want to do, we would like to set each and every one of those constant terms inside of those binomial coefficients equal to a 1. Okay, well, that's pretty lovely. We are getting closer and closer. So I would like to say it's going to be equal to something, 1 minus something times 1 plus something, 1 plus 1 second something, and, all the way up to infinity. Lovely. And now we have to plug in the roots right here. So the roots, the places where this polynomial is going to be equal to 0. But the problem is that it's pretty hard to see where this infinite polynomial is going to be equal to 0 at, well, any given, with even provided that it's not going to be. And infinite series is pretty tough to do because of this, like x to the 6, x to the 4th, and stuff like this. So we're gonna be focusing on the left hand side, the sine x over x. When is sine x over x equal to 0? Well, sine x over x is equal to 0 whenever sine x is equal to 0. But sine x is equal to 0 whenever x is equal to some kind of an n multiplied by pi, where n is an integer. Yes, so when n is an integer. It doesn't really have to be a positive integer, it just has to be any integer. Okay, well, that's nice, because that means that we can pretty much just factor this guy with the roots like x divided by pi and negative x divided by pi. Okay, well, that's lovely. And then going to n being equal to 2 on negative 2, we can factor it further and further into 1 plus x over double pi multiplied by 1, oh sorry, I wanted to do that in pink, 1 minus x over double pi. I'm going with plus n minus here for every single value of x, that's just because n here does not have to be a positive integer, it just has to be any kind of an integer. Okay, lovely. And so we actually have our product form. I wanted to do this one in pink. We have our infinite product of binomial coefficients that's gonna well, multiply out to be this guy right over here, the Taylor series expansion for sine x over x. But now, what would happen if we just kind of multiplied out all of those guys, but not all of them at once, because well, then we would just get this polynomial. But I mean, let's say in couples, because if you're well good with your I think it was product formula, something like this in English, you probably can see that this guy right here is just a difference of squares for some a and b. And well, just as those guys is also gonna be a difference of squares, and all of those guys are gonna be, you know, behind, not behind, after those three dots right over there. Okay, so let's maybe use this kind of formula and rewrite this thing as, maybe I will do it in pink just for consistency. That's gonna be, well, 1 minus x squared all over pi squared. Then it's gonna be 1 minus x squared all over 4 pi squared. You know, 1 minus x squared all over 9 pi squared, and all that stuff until we get to infinity, which we'll never do, actually. Okay, but now what we could do is multiply this guy even further out. But I don't really care about the result of multiplying everything out at once right now, because once again that would just end up being our original polynomial. I only care about what we'll get with those x squares. What's going to be the coefficient of x squared? Because as you can see right now, it's probably going to be something that resembles the sum of squares of consecutive numbers. I mean, 1, 4, 9 there. Huh. Okay. Well, actually, it's pretty much true, because when we go out and now multiply everything out, we're gonna get, you know, some stuff here, absolutely. Then we're gonna get x squared, or maybe I write it like this, x squared multiplied by negative 1 over pi squared, negative 1 over 4 pi squared, negative 1 over 9 pi squared, all that stuff, and then, well, a lot more stuff after that, yeah? No, forgot to put those dots there, yeah? And a lot of stuff after that. But now we can just go on and factor out the pi from there. Then what we'll get is just, well, 1 minus 4 minus a quarter minus a ninth multiplied by x squared over pi squared. But the nice thing is that, this guy right here, oh man, I'm not really good with technology. This guy right here is just the coefficient of x. And the coefficient of x well, has to be equal to itself because now you see this negative 1 over 3 factorial is also the coefficient of x squared in the original series, in the original Taylor series expansion. But well, this is exactly the expansion, it's equal. Yeah, those two polynomials are equal to each other, and so the coefficients that are next to x's in certain powers also have to be equal to each other. And so what we will get after, well, noticing all of that is that 1 over 3 factorial is going to be equal to just negative 1 over pi squared times 1, let's say 1 plus a fourth plus a ninth plus all the way up to infinity. But now let's just go on and cancel out those negative terms on both sides of this equation, getting that 1 over 6 is equal to 1 over pi times, well, that's just the sum as n goes from 1 to infinity of 1 over n squared. And now just multiply everything by pi. By pi squared, and you will get pi squared all over 6 is equal to the sum as n goes from 1 up to infinity of 1 over n squared, and is exactly what Euler got in 1734. That's what we got today as well. So what did we do to solve this problem? Once again, what we did is we, for some reason, tell me why, Euler, considered the Taylor expansion for sine of x, and then for sine of x all over x, we did, how do you say it? We did factor it into binomial coefficients multiplied all together. Then what we did is we manipulated those coefficients, grouping them into such products of two binomial coefficients that the product would be a difference of squares by the difference of squares formula. Then what we did is we just considered all of the stuff that's gonna be in the coefficient of x squared after multiplying all the stuff further and further, and then we just said that the coefficient that is next to x squared couldn't have changed after, well, just multiplying some stuff out in this sequence. And then we said that negative 1 over 3 factorial, which is 1 over 6, is equal to negative 1 over pi squared multiplied by the sum we were trying to evaluate from the very beginning. And this resulted in this beautiful result right over there, that the sum we were supposed to evaluate from the very beginning is equal to pi squared all over 6. I hope you guys enjoyed it. If you did, see you in the next one. Bye.